Hello everyone, welcome. Welcome to the Jane Street office. Can you hear me well? Yep. I was told it works well. Sweet. So I'm a developer at Jane Street. So I spend the majority of my day writing functional code in OCaml, which is a functional programming language. And now I'm talking to a room full of functional programmers. So it's a somewhat controversial topic, at least, that the title I chose. But of course, there's a trick. I mean, I do like functional programming, otherwise I wouldn't be here. In some ways, I want to talk about why I think functional programming matters and why it doesn't matter. So, in some ways, this talk is a response to the paper Why Functional Programming Matters by John Hughes from 1988. In that paper, he tries to convince his peers of why functional programming is great and why everyone should switch to use functional programming. And in this talk, I want to sort of argue that yes, functional programming is great and everyone should be using it, but no, not for the reasons that he lists, rather for other reasons. Before I go any further, though, I want to say I don't want to criticize his paper too much. I think he has written a great, interesting paper, and if you haven't read it, I do recommend you reading it. So, yeah. Okay, so let's start with a quick tour of what his argument is, what John Hughes thinks functional programming is about. So he finds three characteristic features of functional programming languages that he thinks are key to their success. Those are higher order functions, purity, and finally laziness. So in a general point of view, as software developers, software engineers, our job is to manage complexity. And we do that by modularizing various bits of code, separating concerns, and composing things into different modules. And Hughes in his paper describes these three features as sort of the glue to make that possible, to be able to separate concerns. So let's take a quick tour of what these are about. So the first one is higher order functions. This is probably very familiar to you what this is, but just in case, for some of you that are new to functional programming, higher order functions are the idea that a function is a first-class value, such that you can do things to this function that you can do to other sort of normal values like integers or floats. So you can like put them in a hash table, or you can pass them to some other function, or you can stick them in a reference, right? So functions are just like ordinary other values. So if we go through a simple example, by the way, this is now some OCaml, so I hope no one is aesthetically too unpleased. I think it should be a fairly straightforward thing, but if something's unclear, then feel free to ask a question. So this is like a very standard function of like this function map that takes a list and then a function f, and it matches on the list, and if the list is empty, well, it returns the empty list. Otherwise, it applies f to the head and concatenates that with the recursive call. Right? Very straightforward. And the type of that function is it takes some alpha list, and it takes a function that goes from alpha to beta, and returns the beta list. So here, this function is sort of like a higher order function because it's passed into another function, right? But the reason this is powerful or this is useful is because it allows you to define your own control flow mechanisms. So if you see, you're always at the mercy of the language designer to what kind of control flow you can use. So in C, you have for loops and while loops. And then if you use Java, you have things like iterators as well. And then if you use Python, you have like things like yield and list comprehensions as well. But all these things are like things the language designer has deemed useful and given to you, right? But with higher order functions, you are yourself able to define these kind of control flow mechanisms. So you have a lot more power in your hands, so a lot more expressibility about exactly how you want to structure your control flow. So another example of why this is useful is like if you imagine you have like a very big function that does lots of things. And at some point within the middle of that function it needs to do one of two things. Right? So, well, you can easily do that. You just pass in a Boolean flag and like you do an if statement and then you do the right thing, right? But now let's say, well, it needs to do one of three things. We can pass in some match statement, there's some variant, and you match on the variant, it's all doable. But at some point, like, it doesn't become scalable, it doesn't become reasonable anymore. So higher order functions let you do this thing of like, at some point within your big function call, you can just sort of hand over control to a completely different function that does its little thing and then returns, and then you can continue. This is sort of a way of allowing you to specify control flow. So the second point that's useless is purity. Purity means that a function's behavior should only depend on its input, so it shouldn't depend on things like some internal state, like a counter or the time of day where the function was called. And the only thing the function should do is return the output it's specified, so it shouldn't write to a file or print hello on a screen or anything. The reason purity is nice is because it sort of lets you reason about functions much more easily, and they behave very well under composition. So pure functions can be composed in the same way that mathematical functions can be composed. So it's a very natural and easy thing to think about. In some ways, you can think about sort of mutation as a communications channel between two parts of your program. And if you sort of one part of the program gets to mutate some shared state, and the other part of the program then sees this, then this is a communication channel. But using mutation to achieve this is kind of sort of an emergent property. It's not actually part of the code you've written of like some functions and returns, rather sort of using some side channel. And that can make code very hard to reason about. Having said that, though, I think the real world is inherently side effecty. So there are side effects. So if you write a real large-scale program, you'll have to do some side effects here and there. You have to maybe write to an exchange or talk to some other system. So while purity is useful at some scopes, I think it's very hard to achieve or force yourself to be fully pure at all scopes. And the final point that you mentioned is laziness. Again, for the people who haven't seen this, laziness is the idea that you have some expression that you define, but rather you don't evaluate the expression at the time you define it, rather you evaluate the expression as you need it, right? So the expression is defined once, but not evaluated at all, and then only when some function starts using that expression, you start evaluating it. And the classic example of this is if you imagine you have a list, you have the function all numbers starting from n, yeah? And then you pass in some n and it generates all the natural numbers starting from n. Well, the easy way to define this is to take n and concatenate with the list of all numbers starting from n plus 1, right? And this is clearly an infinite list, which if you have a strict language and define that, you just have it'll loop forever. But in lazy languages like Haskell, well, this is just lazy and it's just there, and then you can lazily start using this language. Hughes in his paper describes this as a way of separating terminating conditions from their loops. And I think in his paper he gives a very cool example of how this is useful by talking about an API for a chess game. So he says, well, let's imagine we want to find the optimal move for a chess game. And we can do this using laziness by somewhere in our code defining a tree that sort of enumerates all the possible moves on a chess game. And that's a very simple thing to write because you just have to write a move-to-move function that implements the rules of chess, right? It's very straightforward. And of course the tree is infinite, so you could never store that whole tree in memory because the amount of moves are infinite to chess. But you can very easily define it. And then you can have somewhere else in your program, you can just define the algorithm that traverses this tree and tries to find the optimal next move. And the fact that this tree is infinite and can't actually be represented is hidden away from this algorithm. So this algorithm can just operate on this tree as if it was available, as if the whole tree was just in memory. And this is quite nice and lets you sort of separate these concerns very clearly. And if you don't have support for laziness in your language, it's very hard to emulate this. Like the algorithm that is supposed to traverse the tree will then have to on the fly also create the nodes in the tree it needs. And this sort of leads to more messiness. So to recap, Hughes says the 3 reasons functional programming languages are great are higher order functions, purity, and laziness. And we certainly agree higher order functions are great and they're useful and we use them all the time. Purity is useful to some extent, but it is sometimes also getting in the way of writing larger and complex systems. And laziness is a thing that we at Jane Street reach for fairly rarely. So before going on and describing what we at Jane Street think is important, I want to give a very, very brief overview of what Jane Street does to people who don't know. So Jane Street is what's called a proprietary trading firm. That means we trade our own money on sort of roughly all stock exchanges around the world, and we are sort of acting as what's called a market maker on stock markets, which is the idea of always being willing to buy and sell stocks. I don't want to go into much more detail. If you're interested, then feel free to ask questions afterwards or come find me afterwards. But this is as much I want to say about it for now. So from a technical perspective, sort of we do like 1 million trades per day, and we trade on 200 exchanges around the world and have, I don't know, a petabyte of historical data. And all of this is written in OCaml. So let's sort of think a little bit about what is it that we care about when writing code. We sort of mostly care about 3 things. We care about correctness, dexterity, and performance. So correctness is an obvious one, right? So we write our systems deal with billions of dollars every day and trade millions of dollars every day on exchanges. And if you sort of imagine a tiny bug in a hot for loop, well, that can turn out to be very, very costly within very few seconds. So correctness to us is really crucial, especially because we trade our own money. We don't trade some client's money that we then lost. but rather sort of, if we lose all the money today, then we're out of a job tomorrow and we go home. So we do really care for correctness, and we do really value tools that make it easier to achieve this correctness. And sort of as a corollary, we also really care about clarity. So I would argue that writing some piece of code that happens to be correct but is very obscure and you can't actually convince yourself or others that it's correct is almost as bad, if not as bad, as writing just incorrect code. Right? Because if you write some obscure code that you don't actually know if it works, like how much of your own money are you going to put into trade on it? I mean, not very much probably. So we really care about correctness, and we also really care about clarity, and we sort of like some language support to do that. The second point we care about is Dicksterity, which is the idea of sort of having agility or lifting power in your language that allows you to get things done quickly and efficiently, but also safely. The reason we care about this is, in our world, like, new trading opportunities or new trading strategies come up all the time, and we want to be able to do them very quickly. Like, sometimes these opportunities are gone very quickly, and if you're too slow, well, then they're gone. So we want to be sort of able to get out to the market fairly fast. And at the same time, like, new regulations come up all the time. So maybe the regulator's changed his mind and now you need to do this thing. And like, if you don't do this thing by next week, well, then you can't trade anymore. So we really want to be able to like do these things quickly, especially as we have a high systems to developer ratio, so a low, the other way around, a high systems to developer ratio. We do really want to sort of be able to extend our systems quickly and safely. That means we sort of, in our language, we want to avoid any sort of boilerplate, and we want to sort of have support for avoiding unintended consequences. And finally, we care about performance. So we're not sort of what you ordinarily think of as a high-frequency trading firm that sort of cares about speed, and like we're not really in the game of optimizing our speed through exchanges. But to be competitive, you do have to be fairly fast. So like some of our code should be fairly reasonably performant. And equally, if you do some trading strategy analysis and on a petabyte of data, you have to be reasonably fast. You don't want to sit there forever waiting for the results. So we care a lot about performance. I don't want to actually talk about performance much more in this talk. I think it's an interesting topic, and we can discuss it some other time. I think overall OCaml gives us a reasonable performance picture. It's certainly not the fastest. It's certainly not writing C, but it is reasonable. And another thing that it gives us, which we very much like, is the predictability of performance. So in OCaml, I guess you could call this a feature, the compiler is very simple. So if you write some code and you sort of you can get a very clear understanding of what exactly gets executed at machine level. And if you now change that code in some ever slight way, the performance is probably not going to change that much. While if you take Haskell, for example, well, you can write some function that you can calculate benchmark and has a very good performance. And now you change this in some subtle way that's not at all obvious from code review. And all of a sudden, the compiler is not able to do its clever optimization anymore it did before, and now performance is out the window. And there's no way you would have seen that in code review. In OCaml, that's not the case because, well, the compiler isn't as good. So I guess that's one way of looking at it. Yeah, but overall, as I said, like we care about performance. Performance is reasonable. Performance is not a reason not to choose functional programming languages, but I don't want to talk about much more. So if now we say this was Hugh's list of the 3 things that are important, so if here's the list that we think it should be. So at the top of this list, it should be expressive static types. And then we want higher-order functions. We don't care as much for purity, and we don't actually use laziness. So let's talk about the top point, expressive static types. Expressive means things that it's a fairly expressive type system, so you can represent things like tuples, records, algebraic data types, and so on. And static means, of course, that the compiler is checking that you're using your tape safely at compile time, so it tells you what you've done wrong before you actually run it. So with the above goals in mind, let's see how expressive static types help us achieve this. So first of all, correctness. Here is a fairly obvious example that I like to use, which is the idea of a null pointer. So in many, many languages, you have the constant pain of a null pointer. Well, you can write some code and you convince yourself it's true, but of course you forgot the fact in one case, well, this thing could be null, and then you like throw it in some sort of exception. And this is a problem of many, many languages. In fact, Tony Hoare said this thing once about it. He said, I call it my $1 billion mistake. It was the invention of the null reference. I couldn't resist the temptation to put in a null reference simply because it was too easy to implement. And by now, like this is, I think, to some extent clearly considered a mistake. And much effort has been put into these languages to call back some safety and sort of get into a world where there are no more null pointers. But null pointers aren't a fact of life. Like functional programming languages don't have null pointers. So in OCaml, if like the compiler tells you you have a t here, then you really do have a t, and you don't have sort of a t or null. Right? You have only the thing that the compiler tells you. And to be able to sort of encode a null pointer, you have like this thing option, or the maybe type in Haskell, which I'm sure you've seen before, which is like either some of this thing or it's none. So every time you want to use this thing, well, the compiler is going to force you to think about both cases, the fact where it's some or where it's none. So you can't accidentally miss this null pointer reference. And this, I think, ties back to some other reasons too. Like if you, in other languages, you'd have to, without these expressive static types, you'd have to sort of write some comments around your function saying, well, if the inputs are all guaranteed to be not null, then my output will not be null. And you can see some kind of comment on top of a function. It never returns null. But like, how much trust are you giving into that comment, right? Well, with type systems, well, your function, if it can return some or none, it'll return an option. So like, from the type signature, you can see what is the case. And then the compiler will force you to think about it, right? So the other point I want to talk about is Dicksterity. Let's walk through an example of sort of how the compiler and the expressive static type system help us extend our system in a fairly safe way. Let's say we have this bit of code. Let's say we sort of are a system that passes messages from an exchange. Right? So this message is called an execution, and the exchange can send it to us saying something has happened to our order. So it can either say it sends an acknowledgement. Does this thing work? No. So it can either say it's an acknowledgement, which means, oh, I've received your message, or it could be an out, which means like, oh, your order that you've previously sent me now is no longer live. Or it could say, well, the order you sent me now actually traded, and you got a fill, and here's the size and direction that you got filled on. Does that make sense? So the idea is, well, let's say we have this message type somewhere and we pass our messages from exchanges. And then somewhere else in our code base, we want to keep track of our positions. So we do that by matching on the messages we get from the exchange. And well, if it's an ACK on out, position doesn't change. But if it's a fill, then the position changes by this much. Right, it's fairly straightforward. Now let's say, well, exchange actually gets back to us and says, well, you can also get a bust, which exchanges do send, which is this thing of, well, it's a message that says, the fill I've previously told you about, never mind, it's actually not a fill, sorry about that. And these things don't happen that often, but they do happen like fairly regularly in exchanges. And we're not terribly excited the fact that they happen, but you have to deal with the fact that they happen. So now let's say we sort of add this thing to our variant type here because there's another message we need to pass. And now the compiler is going to give us an error in this other functions, which might live in a completely different place in the code base, saying, well, actually, you've not thought about one case here, right? So now it says, well, in this case where you've matched, you've not thought about the case that is a bust. And this is a really useful way of doing things. And like, I in fact use this all the time when writing a new feature or extending somehow an existing system of sort of add a new variant type and let the compiler tell me all the places I now need to go and think about new behavior. So I want to talk about one more example of a way that expressive static types are useful. So for this, I want to talk about an example, some sort of example function. So let's say we have this function merge, and what the function does is it takes two maps, which are like map or dictionary, both of which have a type, a key type, just be k, so some sort of like say an int or string, and has some sort of value type. And it also takes in a function which takes the value, for each key of the map, it takes the values of both of them, of course there could be none, and it returns some third thing. And now, in the end, I want to sort of build a map which is sort of exists of all keys that are present in either of these maps and all values that are returned by this function. Does that make sense what this function is meant to do? Even if it's not entirely obvious why it would be useful at all. Okay, let's say we have this function, and now we say we want to use it in some way. So here's a very straightforward way of using it. Well, we merge our two maps M1 and M2, and we find this function that sort of like takes A and B as sum, or if there's both present, it takes some F and applies them to both our A and B, and F is defined as some function. Can someone see like what's weird about the way this was used? Sorry? Why? Oh no, sure, but like this is a way of using it, right? Now here I'm not defining, I'm using it. So like I get to define what what the v1 and v2 are. But yeah. Any idea?
What's the type of F, A, B?
Let's say it sort of matches. Like let's say A and B are both ints and F is an addition or something. So that's also fine.
The first case, no, something happened.
Yeah, that's right. This case is obvious. Like this case can't actually happen. Like how would we have gotten here to a non case? Right? And in fact, it wouldn't have mattered. Like we could say assert false on this side, and like that'd be fine. But it's not immediately obvious that this is the case. And this is somewhat annoying because there's an impossible case to reach, and like it would be kind of nice if this code doesn't exist. So we can restructure this by like defining our own types to get rid of this impossible case. So we just define our own type to be sort of a left, a right, or both thing. And now this function takes in this type and matches on it, so that it could be either left, or right, or both. And this non case is now gone. And that is sort of really a great win from a complexity point of view. From managing complexity point of view, this is really, really important because it makes the code more self-explanatory. Like it's more obvious what's going on. Your code reviewers and yourself, you don't have to convince them that this case of non is indeed impossible, and you can indeed write assert false there. And finally, it also prunes branches of the combinatorial explosion of all code paths very, very early. Right? So this is clearly a thing that you want to do very early in your program. And I think this is sort of neatly summarized in sort of the final big statement I want to make, which says you need to make illegal states unrepresentable or impossible to represent. The idea here is that whenever you have some sort of mutual disjoint states that cannot mutually disjoint values in some sort of state object, then your types should somehow represent the fact that some combinations are impossible, and it should just not be impossible to represent a value of this sort of illegal state in your program, in your types. So in other languages, you can sort of, again, carefully maintain this invariant by hand by saying, well, given that these things on its input are all valid, my function does not change then ever into an invalid state and so on. But again, this is very, very hard to maintain. So instead, if you push these things into the type system, you don't have to think about it, and these invariants are just sort of enforced by construction. So one classic example of this is if you sort of think about you have some sort of network module and you have some sort of connection and you have sort of a record type, or in C you could think about it as a struct, and you keep some bunch of information about your connection in there, like the state and some server and some ping IDs and some timestamps. And now some of these, not all of these values can be sum at the same time, right? Like some of these stuff is mutually exclusive. For example, if the state is connected, well, when does it mean to have this when disconnected time set? Is that like from the last time it was disconnected, or the next time it's going to be disconnected? Right. So, or maybe what does it mean if I'm disconnected in the last ping ID? Like maybe I haven't had a ping. So these are kind of non-obvious things, and you ideally want to encode the fact that not all information is relevant in all states. And the way you want to restructure this is by, so for example, in this case, explicitly saying in your variant types what information is available in each case. And now the disconnected case only has this disconnected time, which does not appear in the other ones. So in fact, when disconnected can now not be sort of none, or is enforced to be none in other cases. Right? And now you've sort of encoded this fact in your type system, so there's no way that you've broken this invariant accidentally at runtime because, well, the types make it impossible to represent. This also sort of ties back a little bit to what I said earlier about correctness and clarity. This code is much more obvious, and it's much more easy to understand what's going on, rather than sort of these carefully maintained invariants of this thing is null when I'm in this state, and I promise you it's always true. So to wrap up, we have in our view, our list is this, and laziness is sort of at the bottom of this. Laziness can be useful in some cases, but we just don't reach for it very often. And the reason we don't like it is because it makes performance very hard to reason about. Right? So laziness is tricky to think about, and your function can change in a very non-trivial way depending on laziness throughout your execution. And sort of an anecdotal thing of this is, especially in the stock market where things are very volatile, things are very unpredictable, laziness can really come to bite you if the function that you've run a million times a day before always has the same kind of performance. Now all of a sudden it executes in very different circumstances which you haven't seen, and because of laziness is much, much, much lower. And turns out, well, unintended volatile times of the day are also the times of the day you really do want to trade, and your system should really be up as much as possible. So we in Jane Street tend to not use laziness. We do like purity, and some support is nice for it. OCaml definitely also has support for purity, but if you sort of force yourself to be pure, and by forcing yourself to be pure, you've introduced more complexity, then you've sort of lost, right? You don't want to trade purity for complexity. You always want to reduce complexity. And in some cases, purity is just sort of more complexity that you don't want to have. We definitely love higher order functions. They're great. But at the top of our list, no doubt, is the expressive static type system and all the benefits it gets from it. Luckily, we don't really have to choose because in OCaml and Haskell, you kind of get all of them. But there we go. If you had to choose, this would be how we choose. So this is also all I had. So I'm happy to take some questions, or if you're willing to sort of find out more about this, like we have a website, of course, and we also have a GitHub page where a bunch of our stuff is open sourced. Thanks.